Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're very happy to have Paul Cuff back from Stanford, and he'll tell us about investigating the fundamental network burden of distributed cooperation.
All right. Thank you. Well, it's good to be back. I'm going to talk today about the communication requirements to set up cooperative behavior. And the examples we'll use will be a computer network where you want to distribute some computation among the computers in the network. Many examples could apply. Could be talking about UAVs coordinating their flight patterns or something. But we'll look at a very simple model just to see how information theory tools can be used to analyze the communication requirements in some of these settings. The first half of my talk will just be about, the goal will just be to distribute these different computations. The second half will be looking at an adversarial setting and what changes, trying to relate it to encryption if there's an adversary. And in between, we'll do a short break. Since it is the theory group, I have to do something on the whiteboard. But, okay. So this is an artist's rendition of a data center. Let's say this is one of Microsoft's data centers around the world where they're doing some cloud computing or something. In fact, let's just, so these are a bunch of computers in racks somewhere, and they're networked together with some cables. And let's say some requests, maybe a search request comes into a buffer. And so you buffer up all these requests, and then they're distributed out to the computers in the network. So I assume that Microsoft probably does it similar to how other companies do their search, where a small portion of the search is done on various computers so they can quickly get the results and send them back. And so, the search request would be farmed out to these different computers, and they'd all send back the results, and then you send it back to the person who searched for it. So the question is, in a setting like this, what are the requirements, how much needs to be sent across these network cables in order to get the various parts of the task done at different computers? Let's look at it. We'll look at a really simple model. We have computers in some sort of communication setting, and each one of these boxes represents a computer. No, did I say they're assigning? They're assigning tasks, and what happens is some of the computers will be given, so the tasks will just be numbered from some set. They all know what the number corresponds to as far as what computation they have to do if they're assigned number 3, so forth. And some of the computers are given their assignments, and other computers get to choose their assignments based on the communication they receive. The goal is that no two computers do the same task. Okay. We'll look at a sort of cascade network and a network that you might call star network as examples of how we might analyze this. Okay, so what do I mean by assigning tasks? Well, let's start with the 2-node case just so we're on the same page. Okay, here's a computer who gets a task assigned. In this case, there will only be 2 tasks, task number 1 and number 2. So 2 different parts of the computation. This computer is assigned to do task one of the 2 randomly. This computer then needs to pick the other task. Okay, how many bits must be sent through this network in order to achieve this? This is not too tricky. Anyone want to venture a guess? 1 bit, right? You say which task you're doing, they pick the other one. Okay, suppose that there are more tasks. Same problem though. This computer just needs to pick a different task. How many bits might you need now in this network?
one task at a time, or you need to assign k over 2 tasks?
What was that?
You need to assign one task to each computer, or k over 2?
No, just one to each computer. So they just each need to do one task different from the other one out of the k. That's all.
You just have 2 computers here.
Just 2 computers in this case.
It's less than 1.
Okay, less than 1, right? I was trying to trick you into saying log k, right? If you wanted to say what task this is, you would need about log base 2 of k bits to say what task it is, and they could pick a different one. But you certainly don't need more than 1 bit. One way to do that is just divide the tasks in half and use your bit to say whether you're in k over 2, the first half or the second half, and they pick from the opposite half. But like you've all said, you can do much less than 1 bit. Let's see what we mean by doing less than 1 bit. Okay, so we'll use the common information theory assumption that we're actually buffering a lot of tasks. And at each time epoch, we have this same problem where we want the other computer to choose a different task. But from time to time, it's a new independent problem. We just want an independent assignment of tasks that are different. Okay, so we have a long buffer coming in, and we want to solve the problem. But we're allowed now to, notice that I said bits per task. We're allowed now to save up our bits, okay, and use them all at once. So, for example, let's let k equal 5 for this example. So the tasks are 1, 2, 3, 4, 5. Here's a sequence of independent task assignments coming into the first computer. And he might take maybe 8 of them. And let's see what, suppose the rate we're trying to use is 1/4. Okay? Then with 8 symbols, you now have 2 bits to work with. Okay? So based on this task assignment, the encoder, the first computer, will send 2 bits to the other computer. And that computer will have 4 possible received messages. Each message will correspond with the sequence. So it's a function from these bits to a sequence of tasks for computer 2. Right? So this we'll call a code word out of this entire thing, which is the code book. And the idea is if this was the code book, then the encoder would look at this sequence and say, well, there's a 4 and there's a 4. This second sequence certainly doesn't work. Okay, so I'm not going to send the message 0, 1. But we see, if we compare every bit with this first one, they're different, 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 different. Okay, it works, right? So you can send the message 0, 0. The decoder will then choose a sequence of actions, and you'll have accomplished the goal. So for each code book, there's a probability of error. There are some sequences where you won't be able to find a message to send such that it'll be different in every place, right? So that probability of error for a given code book, what we say is that a rate now is achievable. Here we were looking at rate 1/4, but a rate is achievable if no matter what probability of error is demanded, say 1 in a billion, you can find a buffer size n and a code book that gives you less than that probability of error for any probability of error. And it's not achievable if no matter how long you look, you'll always have some error. Okay?
You're always assuming independent uniform.
Yes, for this problem. The same analysis would work for other things, but for these problems, we'll always assume that. So the problem for the 2-computer case is solved with rate distortion theory.
With what?
Rate distortion theory. And so let's see what the answer is. The minimum rate needed is the mutual information between x and y. Now, x and y are random variables, where the distribution on x is given by the problem, uniform 1 through k. You get to pick the distribution p of y given x to minimize this quantity, but the constraint is that x and y cannot be equal with probability 1. Okay, so this optimization problem will tell you the minimum rate needed in that. And mutual information is the sum of the entropy of x plus the entropy of y minus their joint entropy. And entropy is this expected value. So let's just work out what's going to be the minimum one for this problem. I think I'll do it over here. Let me propose a p of y given x. Let's say, I'll give you the p of y given x that minimizes this, and then we'll show it actually does. Okay? Let's let y be uniform over all the choices not equal to x. Okay? So then we have I of x, y equals, so h of x is just log k, right? H of y is log k. Whoops. And h of xy, now this is a sequence of two non-equal numbers out of k. So here we have k minus 1, right? The entropy of xy. Yep, good. Okay. And so that equals log k over k minus 1. Okay? Now, is that the lowest? Well, let's write mutual information another way. H of x minus h of x given y. This is another valid way to write mutual information. This is fixed by the problem. We have no choice in this, so this is going to be log k. Yeah, here I was doing it the first way of expanding that's on the slide.
Right. Y eventually is uniform over 1 over k.
Yes, yeah, it is when you marginalize out x. So then here we want to minimize this, so we want to maximize this. So what's the most that it can be? Well, h of x given y less than or equal to. We know that it's not equal to y. So this only has positive mass on k minus 1 entries, so it's less than log of k minus 1, right? So there we go. That minimizes the mutual information, right? Okay. So as you've all said, it becomes less than 1 bit. If k is 2, then it's 1 bit, right? And it goes down significantly. Okay. This is approximately 1 over k bits. Right? Okay. So now let's look at it in this sort of cascade network. Now there are k computers total. The first one is given an assignment. Okay. The next k minus 1 computers all get to choose their task based on this communication that's done kind of in a daisy chain like this. So now what rates are needed so they can all choose different tasks? They're going to all the tasks are going to get assigned in this problem. In this case, we know the minimum rates. And it's done in the following way. You first assign the last computer a task using the rate we just talked about, log k over k minus 1. Then, since that communication went through all the links, everyone knows what that task assignment was. So now all the remaining computers kind of reduce the set of tasks by 1. They say, oh, the last computer is doing task 5, so none of us are going to do 5.
K computer will k task.
Yes.
You have to pretty much transfer the full information.
Yes, certainly across this link here, you're giving all the information. But not necessarily across these, right? Because, so...
No, why not? Because you have to... okay, I see. They have to tell only which to what, and they have to do... it doesn't have to tell which one is done on what.
Yes.
So it will save some...
Yes, exactly.
I mean, the last one doesn't need to know anything about the others.
Yeah. So optimally what you do is you just send the last guy his assignment, and since everyone else heard it, they'll reduce the problem size by 1, and you peel off the next one, but now it's changing k to k minus 1. Okay? So the way you prove that this is optimal, well, first of all, let's look at how much rate on each link. This link only has this communication. But the next one back, r of k minus 2, is the sum of these, right? And so forth. So what we get is that Ri is just, when you do this summing up, you get log of k over I. Okay? And what we can do is we can show that this is actually a lower bound individually for each link just by looking at the mutual information between x and everything past it, which can now be unordered. You don't care about the ordering. Okay, now let's look at the sum rate in this network. At first glance, okay, I cheated and gave the answer away already. Okay, at first glance, this it looks, it's a pretty bad network in the sense that the message you send to a computer has to go through many links. So it may look like the communication scales with maybe the square of the number of computers when you add them all up, because the communication to any computer passes through a number of links that's linear in the size of the network, right? But when you add the log k over I up, take out the k log k, and notice that the sum log I is log k factorial, which can be approximated by k over e to the k. Now the k to the k cancels this, and you end up with the k log e. All the logs we're using are log base 2. Okay, so we're using log base 2 so that we can call it bits. Anything, you can use any log you want, but no one works. I don't know a computer that uses nats for their base arithmetic. Okay, so it's linear in k. Okay, so that's kind of nice. It's just log 2 of e is 1 point something. Anyone? No.
But this problem you can just do the usual one that they have to just tell which set is gone so far. So that it matches the same bound. Every link you just have to inform that which set is gone so far, which set of jobs is occupied.
Oh, I see. So you're saying tell this guy what you have. Well, okay, but you don't want to tell him a set. Oh yeah, you do. Yeah, you tell him. Okay, you tell him what you have so far, right? But that would suggest that these rates would go up, right? Because then here you would have to tell him these 2 assignments. If you did it that way, where you say, I've got assignment 5, and the next computer picks his task.
Yeah,
he picks.
The permutation, which is typically why you just tell, but.
Yeah, you just tell the set, so you get rid of the ordering.
Yes.
Yet still that would go up. It would still go up because you would get k choose 2, log of k choose 2 here. Right?
But that's the essential information they need to know.
No.
Yes, so I'm a little
Because
bit
they have to
confused
make
about
it think
what
which is
information
different
you
from
do
others.
actually send, even in the 2-computer case. right?
Okay,
Because
yeah. See, the trick with the 2-computer case is you can't understand it by looking at it one letter at a time, because there's no message about just that one symbol. So you just are identifying a sequence that works.
No, but this 2-computer case that's not the generalization because they are k and n are equal, the number of computers in k. So at every point you need to know which set is wrong.
But you still have to know what this first very long arrow means, right?
Yeah, this thing here.
And it means, you're saying it means something complicated that says you wait for a long
Yeah.
number of trials
And then
go
you
for-
just tell them a sequence that works.
But that's I'm not saying that you should, but
Yeah.
that's the essential information you need to convey on every edge, that which set is available for the rest of the guys.
So if we look at I think the key is you're looking at the second rate and saying, okay, how do we get this smaller? Because this is smaller than this, right?
I'm not saying smaller, I'm saying this is the essential information which has passed through
He's
it.
getting something more efficient than that.
Yeah, because what I'm doing is I'm assigning, basically if you look at the message on this rate, on this link, you're basically assigning all the rest of the guys unordered without assigning this yet. It's like if you already assigned this, then you have to convey more information.
Jobs are assigned. Those jobs will not be assigned further. So, and furthermore, all the jobs will be assigned because
Yeah.
these cases are different. So essentially, whatever project you are doing, this and exactly this information is passed on this channel that what jobs are gone.
No, because you assigned the last one.
Starting from the
So
end.
first you tell the last guy what his sequence is, and then...
Oh, so you are not assigning this guy and then
No,
this guy?
no, do it in reverse order. And it saves the rate that way. So,
But you can't think of it one trial at a time, right? You
No.
really have to think
you have to think of this, you have to buffer it up to really get these rates. Yeah. So this is, so you get basically log base 2 of E for each computer in the network. Okay, let's look at it.
Running time, you have to wait a lot, and it's quadratic.
The-
Because you need to do it sequentially. Or can you do it in pipeline? I mean, or you need to wait until...
The idea is you would wait like for...
You need to wait till the buffer size.
Okay, you would always be behind a little bit or something. Like you would have to know your task assignments ahead of time. The question is how do you actually the question I've made out of this is how do you actually do a block coding with task assignment? The first computer would have to know its task assignments ahead of time. And after it's waited for its block of 100, it would send at a low rate for the next 100 that it's receiving. It's receiving the next buffer. And it would be using that time to send the information from the previous block. And then they'd all execute.
About the buffer, I'm talking about, the information transferring through the network. Say you already buffered.
Oh, I see. Because you're like, you now know what the messages are, but you have to send here and then send here and then send here to the delay of going down the network. Yeah. So I haven't considered like yet that you would, if you count the delay for each link, then that would affect things. But of course you can pipeline, like you were saying. Yeah, you could pipeline this. Okay, so very similar, but what we're going to do is say the first k-1 tasks are assigned. Okay, for some reason they know that their task assignment is rigid, and you only want to know the last one. Now really the idea would be that you would want to know some of the tasks are assigned and some aren't, and what's the answer. But we're looking at the simple cases first. And this case actually turns out not to be very simple. But so in this network, the last computer, the task that he does is fixed. Like it's the task that all these guys are not assigned, right? So there's no flexibility here. He just has to know enough information from the rest of the computers in order to figure out which task it is that's not being done. Okay, but so we don't know the actual optimal answer here. But let me propose one idea. It's like what Kamal was saying. Send here the information about what task you're doing. That has to be done. We know that must get across somehow. You save a little bit because you use the side information that this guy knows one task is eliminated. You do slep-in wolf coding. So you save a little bit of rate. And the rate needed there is log of k-1. Okay. Then here, this person, he looks at, this computer looks at both these tasks and gets rid of the ordering because that doesn't matter. So saves a little bit, saves 1 bit by getting rid of the ordering, but basically transmits this set to the next one. And they keep going so forth, like that. And then the rate you would need at each one is k-1 choose I. Okay? Now this is kind of a strange scheme because it's totally different than the network before. Now we get rates. Consider this a graph of the rates in the network. They peak in the middle, right? So you need really high rates in the middle and not very high at the edges. Plus, all of these rates are already very high. I mean, this is worse than log k for log k-1 for every link. Now this is one scheme that seems reasonable. It's not. We could also go through and minimize each rate, each link individually, and you'll find that this is not necessarily optimal. There's a whole trade-off. If you allow for higher rates on some links, you can then get away with small rates on other links. Okay.
For example, you can get an equal rate if you just always transmit the sum of the numbers, and the last one will just get the k times k plus 1 over 2 minus the sum of all previous numbers. Then the rate will be fixed.
Interesting. Okay. So you do like the mod k sum or even just the real sum? Just the real sum. Mod k, fine, either one. Interesting, yeah. I wonder what rates we would get in that case. That's nice. That's nice.
What's the upper bound you got from
Is this. That this is an achievable point. Okay, but it's a whole region, right? It's a high-dimensional region because you could always trade off rate 1 for rate 5, But so in the first case, there was an optimal point. The region was rectangular, and there was one optimal point that summarized everything. In this case, there's a lot of trade-offs, and this is one achievable point in the region.
If you're trying to optimize the sum of the R.
Okay, then yeah. Exactly. So if you're trying to optimize the sum, I mean that scheme would be interesting to look at. Like what does that take? So that at worst would be like log k for each one.
If you don't want
Right. Okay.
So if all these x1 to xk-1 are assigned, they don't need to communicate with each other, just with y?
They just need to communicate with y, but the thing is the only way this computer can communicate with y is through the others. Okay? So we're looking at saying the connections are fixed. If you change the connections, then yeah, you would want, probably, you would just want them each to go there. Although it would still be a challenging problem, actually. Okay, so if you minimize each rate individually, you find that the rate needed on each link is just log of I plus 1, so that actually suggests that might be a interesting scheme. No, but this does a little bit better than log k, right? Because for the first ones, you're much smaller. I is smaller than k. So this is not achievable. In fact, I think this is far from achievable. This is just saying that the smallest rate you need on the first one is log 2. You don't need to send actually the whole thing. What you can do, what you do basically is you say, okay, I'm going to assume that these rates are really high. So the last computer knows all of these assignments. If he knew all of those assignments, he can use that side information to greatly reduce the rate with which I need to send this, and I can get away with only 1 bit, right? So using those types of bounds, you get a lower bound like this, but still, the sum is still k log k. So even with these lower bounds, you're getting worse than the other network, which seems kind of funny considering that there's only one task being assigned in this network, and the other ones had a lot of tasks assigning, right?
So does your proposal achieve this?
No. No, mine I think would be more like k squared.
But yours is
This one here?
Yours is up to this.
No, but this
over
one does. Yes.
Up to this over e that you've got there.
Exactly. So yeah. So divide it. Yeah, exactly. So up to the k log e. Nice. So let's look at this last one here. So we have this star-shaped network. And basically what we have here is the guy in the middle gets a task assigned, okay, and can communicate directly with all of the remaining computers. And each of those computers gets to choose its task. So you may try here to go back to the 2 computer limit. We knew that with 2 computers, it was log of k over k minus 1, right? So what if I just use log of k over k minus 1 for each of these? And that doesn't work, but it will guarantee that, for example, y2 doesn't equal x and y1 doesn't equal x, and each of these will be different than x, but they won't be different from each other necessarily if you try to use that communication scheme, right? So what extra needs to be sent to make sure they're all different from each other? Okay, well, one idea that actually works quite well is the following. You say, let each of these computers have a default value, okay? So this computer will do task 1 by default and 2, and so they have k minus 1 defaults, and k is not a default anywhere, right? So if x gets assigned k, then good, they're all fine. If x gets assigned something else, like 3, then all he has to do is send a message to this computer to say, move out of my way, and this computer knows to then go take assignment k, right? So now what rates are needed? Well, you just have to know how frequently will you be telling an individual computer to move out of the way. That's 1 over k. Right? So sending a bit stream that's 1 over k of the time, that takes a rate of h of 1 over k, where h is the binary entropy function. It's just negative p log p minus 1 minus p log 1 minus p. So it's the entropy of a Bernoulli random variable. It's approximately log k over k. Okay? So already we're seeing that this scheme is going to be very good, because when you multiply it by k, you're going to be less than linear, right, for the sum rate in the entire network. But I have to mention a scheme that works even better than this. The reason is because the answer is so nice. But let's look at, so you've all probably thought I only had one talk that had the golden ratio in it. Okay, so let's look at just the 3-node case of this network. All right, so this computer gets assigned to task 1 through 3, and then these 2 need to be different, right? We can make an improvement over this default scheme. I mean, he could take a default 1 and a default 2, and we know how that works. We can do an improvement by first sending an estimate of x to them. And the reason this is, okay, so in other words, you send, at a very low rate, you send a guess of what x is that isn't usually right. It's only right slightly more than it should be, okay? So these 2 computers have a guess at what x is to work with. Now they're going to pick default values centered around that guess, okay? So in other words, if the guess was 2, then this guy's default will be 1 and his will be 3, okay? Something like this. Now they go with the same original scheme where this computer then, on the second round, so it's like a 2-stage communication. First stage is send the estimate. Second stage is tell them if they have to move out of the way. Now, because of the estimate, they'll have to move out of the way less frequently, right? So there's a trade-off of how good of an estimate do you send of x, and how much do you save from not having to tell them to move as often? And you optimize that with calculus, and you get that actually the optimal rates with this scheme are log 3, which is what it would take to send x exactly, minus log of the golden ratio. And the golden ratio is the square root of 5 plus 1 over 2. Doesn't come up too often in communication problems unless I'm working on them. Right? But there are golden ratio fanatics who who see it in pine cones and everywhere, right?
You started with those and divide the problem.
Exactly.
So sending an estimate is somehow shorthand for something else, right? Because, you want it to use less bits.
Yes. So it's like sending the estimate. The thing is, when you send an estimate of x, basically what you do is you devise a joint you use the same rate distortion type of results, and you say, you get to pick, the rate is going to equal I of x hat. This is the rate you're going to have to use to send the estimate. And you get to choose, so p of x hat given x, p of x is fixed. And the receiver essentially is going to get x hat. It's going to come in the form of some long sequence and stuff, but essentially it's as if the decoder knows x hat, and you only needed to send it with this much mutual information. Now the cool thing is, so the distribution is going to be something like this. This will be like, 1, 2, 3. This would be something like p of x hat given that x equals 2. Okay, it would be like, some probability, some conditional probability mass function where it's slightly more likely that x hat equals x, right? But the mutual information is like, you're when this is uniform, you're at the peak, and so you're quadratically getting penalized based on what conditional distribution you use. So you're not paying much. In fact, when you optimize this, the rate, so this total rate's like 0.9, around 0.9. The rate of sending the estimate is 0.04. So you hardly use any rate, yet you get away with reducing this probability here. And so the savings are kind of linear. It's like the penalty is quadratic, the savings are linear. So that's why it works. So, okay. So for this part of the talk, we looked at these 3 networks, and what we noticed anyway in the first network, we could analyze it exactly, and the sum rate was linear in K. When we went to the second one, where a lot of the assignments were given already, and you only had to assign the last one, the rates got worse. We saw that R min is kind of K log K, and we were given a scheme here during the talk that gets that same scaling, right? And then in this last network, we don't know the answer, but we do know a scheme. So we have an upper bound on the minimum rate because we know a scheme that works.
So this two-stage thing only improves the concept.
Yes, it's not. There's no lower bound on that to say that that's actually optimal, at least.
So then if you did the naive thing, you also got
Same. Yeah, you also got
so
log
you
K.
got a better concept with the two.
Yeah. So.
And you know that you need at least oligophlock, for the.
I don't know that. Yeah.
So what lower bound is known?
Oh, okay. We know that you at least need the two computer limit, like if none of the other things were in the network. So log K over K minus 1. But see, that's going to be like constant, right? I mean, what? No, log K over K minus 1 times K. How does that scale? It's what? It's constant. So the lower the lower bound we know would be constant scaling. Of course, log K is already pretty nice. But okay, so okay, great. Time for our intermission, and since I'm taking too long, we don't have that long. But I want to. We're going to move into like an adversarial setting, but I thought because this is the theory group, we might enjoy a little puzzling question before we move on to this part. Okay, so suppose you have some random variables, two sequences, x1 to xn, y1 to yn. I'm going to abbreviate these as x to the n, y to the n. Okay? I'm not going to tell you their joint distribution, but I'll tell you something about their joint distribution. Okay? And the question will be, if we have some Markov chain with a variable in the middle that separates these entire sequences. Okay? So conditioned on u, the random variable u, the sequence x1 to xn is independent, conditionally independent of y1 to yn. Okay? And I'll want to know something about the cardinality of u. How big does the cardinality of u have to be? And it'll tell us something about, what's the connection between xn and yn? Is this minimum cardinality we need on u to separate them? Okay? So let's say the cardinality of u equals 2, it's going to be exponential in n. Okay, so let's say 2 to the n r. Okay? So we want to know what r is necessary as n gets really large, and as I give some constraints on the joint distribution of xn, yn, what r will be necessary. Okay, so the first question, so there will be 3. First one is, so the first thing I'll tell you about xn and yn is the following. Let me define a typical set. Okay, so typical set. This isn't. I'm not going to have room here. I'll do it on the other side. Okay. We have a p naught of xy. Don't be confused to think that this tells us the distribution of x and y, and it's just a joint distribution. Okay, xy. And the typical set with respect to that joint distribution, epsilon n, is the set of xn, yn sequences such that the sum n, 1 over n, sum, the indicator function that xi, yi equals ab, a comma b, minus p naught of ab. This absolute value is less than epsilon for all ab. Okay, so all I'm saying here is that the empirical distribution of these sequences, okay, this here is the empirical distribution of xn, yn. If you count them up, just looking at the pairs, and you look at their distribution, that is very close to p naught of ab. Okay, so this set is all sequences whose empirical distribution is close to p naught. Okay, and I'll call this typical set. Now, all I'm going to tell you about xn and yn first is that with high probability, greater than 1 minus epsilon, they are in this set. Okay, so for the first step is simply that I'm saying that the joint distribution of these two sequences is such that with high probability they're typical according to p naught of ab, p naught of xy. Okay, what cardinality do you need for u? Now this first one's sort of a trick question because xn and yn, they could just be a deterministic sequence that is in that set. Okay, so if they were deterministic, then they're already independent. So you don't need anything to separate them. Right? No, given this information, what's the best as far as lowest rate? Okay, so given that information about their joint distribution, what's the lowest? You can pick the joint distribution, and you can actually pick the joint distribution even with u, right, to minimize this. Okay, and then you get that R equals 0 because you can just have a deterministic sequence. Now let me add one more thing, okay? Let's add that. So the first one was that xn, yn are in T with probability, 1 minus epsilon, right? Okay, so, and we saw that, R equals 0. Okay, next one, same thing. But also xn is distributed IID according to P naught of x, according to marginal on x. Okay, so now I'm telling you a little bit more that this is actually IID. Also, they're jointly typical with high probability. Now, what is the minimum U that separates them?
X is IID
with the marginal distribution of P naught. P naught is the same P naught that was used to define the typical set. X is also IID with that distribution. Anyway, I'll just give these answers. So now the minimum rate needed is the mutual information between X and Y. Okay, and this relates to coding theory because it's rate distortion theory because X is like a source of information, U is like a description about X, and there's no requirement that the reconstruction is actually random, but you do require that it's jointly typical. So you have this Markovity naturally from describing X and then decoding it. So this is just another way of looking at rate distortion theory. Now the last one is that. Can you see this? Yeah. Okay. That xn and yn are IID according to P naught of xy. Okay, so that's what I'm telling you about the joint distribution now, is that these are actually IID according to P naught of xy. Now you get to pick a joint distribution with U that's Markov and try to minimize the cardinality of U, okay? And this one, the answer, it's not mutual information, although I know many people to guess mutual information here, but no, it's that the rate is greater than what I'm going to refer to as the common information between X and Y. This was defined by Weiner, this term, common information. And what it means is so the common information between X and Y is the minimum mutual information between the pair XY and some other variable U where U satisfies the Markovity XUY. So this is just a single, this is an optimization problem. You just look over all U that separate X, U, Y. You may think, well, this looks a lot like the problem we were just looking at, except for that this mutual information is very different than you might have guessed is the answer, right? It's mutual information between the pair XY and the U that's in the middle, okay? Anyway, so this common information will come up in the work we're doing, so I thought this was a way to introduce it. What?
What is, you can a priori bound the size of U.
Oh, yeah. So U, okay. So when you do this optimization, you only have to look over U of size, I think, X times Y. So the product of the cardinalities is minus 1 or something like that. Still pretty big, I guess. Okay.
But it's calculus, not functional.
Yeah. Okay, so what's this picture of? What?
NSA.
The NSA, yeah. Okay, great. So let's look. We're going to now talk about coordination of behavior in an adversarial setting. Okay. So, what is let me describe encryption, the basic problem of encryption, as I see it anyway. You have a source of information that we'll call X, and you want to send it with a description to a decoder that will then decode X. Okay? But an enemy sees this communication, and you don't want the enemy to know anything about your information. So in order to do this, you're not going to have luck in this setup unless you have a secret key. Okay. Now these two know the secret key. The enemy doesn't. And this problem was looked at by Shannon, and a very negative result showed that, yeah?
You're ignoring public key crypto?
Yes. Well, what I'm taking away all computational limits. Okay? So we'll just look at it from the information theoretic perspective. So yeah, clearly this is not how encryption is being done because of this, basically because this result's very negative. It says that the amount of secret key you need is as much as the information you're sending, and you can never reuse the secret key, right? So, so the one-time pad, the way you do this encryption is you have a message here, you have the secret key, and you just do XORs of the entire message, right? And you get something that's independent of the message. No matter how long someone sits here and tries to crack it, they'll be no better at figuring out your message, right? And then you undo it with the exclusive OR also. Okay, so then the minimum rates needed, R1, if R1 is the communication rate and R2 is the secret key rate, then R1 equals R2, that should be equals, I need to fix this, equals the entropy of X, right? The rate needed to describe X without loss. Okay. So, yeah, let me emphasize again. So what we'll look at is the information theoretic limits, assuming there's no computational limit. So it's far from practice, although with the advent of quantum key encryption and maybe some realistic ways of actually exchanging long keys, then maybe this will have some relevance coming up. So, okay. Now, I want to sort of broaden the mindset of encryption into a game theoretic setting. Why do you need to send a secret that someone else can't discover? Is there a way of modeling this as a game where the person who might discover your information would use it against you somehow? And if so, then let's look at it in a game theoretic setting. So here's a simple repeated game where you have an enemy who can take one of two actions. And here's me, and I can take one of these two actions. And based on the actions we take, we get a score. And I wouldn't want to take action 0 if it were known I was going to take action 0 necessarily, because then the enemy would choose 0 because he would want me to avoid getting 2 points. And if I chose 1, and he knew I was taking 1, he would choose 1 and get me the negative 1. So it's better, actually, if I randomize over 0 and 1 just right, and avoid him being able to slap me with the worst penalty, right? Okay, and there's a score of this game. Now, suppose that I have a partner on my team. Okay, so our payoffs are actually a combination of 2 actions. Again, we might like to randomize, and the optimal randomization might be correlated between the partners trying to cooperate, right? So let's look at, from this context, let's throw it back into a communication setting, okay? If you have person A and person B separated, acting in a game, and they each are randomizing by flipping their own coins, okay, then their actions will be independent from each other, okay? But if you add a communication link between them, then they can achieve coordinated actions for competing in this game, okay? So suppose an encryption setting were looked at in the sense of you have some sensitive information that affects the actions you're taking in this multiplayer game. You want to send something about that information to your partner, who will then take some actions in the game as well. And you don't want the enemy to know anything about your actions. Okay? So we're going to try to relax. Basically, we're relaxing the requirements of encryption by not requiring that you send your information. The only difference here is that doesn't equal X. Okay? So we're not requiring that you send the information exactly. We're going to try to relieve the rates needed on the encryption and on the communication, but at the expense of only decoding something correlated with X, okay, not equal to X. So now we ask, what are the required rates? We're not compromising secrecy at all. So the enemy can't know anything about X or Y. What are the required rates of communication and rates of secret key to achieve a given desired P of Y given X? Okay.
I just want to question why this perfectly represents the previous problem. You might want to communicate, have a higher correlation,
and give away some secrecy.
Give away a little bit, and that might be better in the game.
Good. So you can actually analyze the game with the way we did it was we say the enemy sees all of your past actions. The enemy sees this public communication, of course, and you do a repeated game, and you say of all possible ways of using communication, you actually show that you can't do better than doing it this way. Okay, so where you keep the secrecy perfect, because essentially when they see. If you leak some of the secrecy, you're not really achieving you're achieving some new conditional joint distribution, right? Secretly. So, okay. So here's the result.
Is it obvious that always keeping the secrecy is better than leaking information because you can ignore the information?
But you can communicate more, correlate them better.
Communicate. That's right.
So there's, I guess I do need to explain one thing. The way, when we actually showed the lower bound that this is optimal for games, we were actually letting, it was a slightly different setting. There was still, this guy actually picked his actions. It wasn't given to him randomly. He generated actions, sent something about it to the partner who generated the counterpart actions. In that setting, this is optimal for games. Okay, there's a nuance when you do this exact setting where this is supplied randomly as sensitive information, and you're describing something about it to your partner. The nuance is that the game might be kind of degenerate in the sense that you just want your partner you don't care about keeping a secret. There's nothing they can do to stop you when you do a certain set of actions. Right? And if the game is degenerate in that way, then you don't want secrecy. You don't care about secrecy, so you just go for correlation. So there is kind of a balance between leaking the secret and getting higher correlation, if in this exact setting. Yeah. So the setting where we showed optimality in the repeated game was slightly different than this. Yeah.
So there must be quite a lot of assumptions about the game, right? Because otherwise, maybe you actually want the enemy to find out everything.
Yeah, so actually that's one thing I think that I'm interested in learning is taking this exact setting, applying it to a game. Okay, in this exact setting, X is better viewed as side information about the game. Okay, X is like some side information. You have a random payoff matrix, and X is correlated to that randomness. And then you say, if you had a partner who was watching the side information and could send you something about it at a certain rate, what should they do to get you to do well in the game? Okay, that's what this exactly applies to, how this would be applied to the game theory. The setting we were able to solve was the one where, rather than side information, this is another action in the game, and you generate it here. It's not given to you. Okay, so.
But you're allowed to use a mixed strategy when you generate the action.
Yeah, you can generate it with a mixed strategy, describe it to your partner, but it turns out that actually makes the problem a little bit easier that you're generating it rather than sending it. Yeah. So it's a little bit subtle, but there is some concrete connection with game theory, but there's also what you've all mentioned actually is relevant too. Okay. So the result is, again, you have this auxiliary U that you get to use in your optimization. Now, we have a trade-off, actually. So it's not just going to be a minimum communication rate and a minimum encryption rate. There's a trade-off. You can exchange some encryption rate for some communication rate. And the rate pairs need to satisfy that R1 is greater than the mutual information between X and this made-up U that you get to use for optimization. And R2 is greater than the pair XY with U, the mutual information between the pair and U. U, again, has to satisfy this Markovity. It separates X and Y in a Markov sense. Okay? So you consider all U, and each U gives you a rate pair that's a set of rate pairs that are achievable. Okay? And but the nice thing about this is, what if we looked at the extremes? So we're going to get a region. It'll be some trade-off region. of R1, rate 1 and rate 2. But what if we looked at just the extremes? What's the minimum communication rate if we don't care about the encryption rate? Okay, well, by the data processing inequality, you could say that's minimized by letting u equal y, okay, but because of this Markovity. So if u equals y, then we have mutual information between x, y. Okay, so minimum communication rate is the mutual information. What if we want to minimize R2 without caring about R1? Well, that's exactly this Wiener problem here. That's the common information. So the two extremes of this region are the mutual information and the common information. It's kind of nice to see these kind of fundamental quantities showing up. Okay. Lastly, let's look at an example. Let's go back to the task assignment and solve it for the encryption setting. So in the task assignment problem, one computer was given a task randomly and just wanted the other computer to pick a different task. What we're going to add here is that you want the other computer to actually pick randomly among the other tasks. Okay, so let me try to give you an example of what we might be trying to do. Say there are a bunch of files and you have a virus scanner that's looking through for viruses, okay, in some network. And it picks and it goes through these files, but you don't want it to go through in a deterministic pattern because you might get some clever virus that follows right behind it and never gets caught. Okay, so what it's doing is it's randomly picking a file to search and then randomly picking a new one. Okay, now you have another process, another part of the virus scanner that's doing the same thing, picking files to scan, but you don't want to be scanning the same one. So what rate of communication and what encryption is needed so that this other virus scanner can randomly pick another task? You're both always randomly picking two different tasks. Okay, that's the scenario here, right? Okay, so you're given the task, you're given yours uniform 1 to k, and you go apply those results, and what you find is that a rate, here's one point that's achievable. Communicating at rate 1 and using encryption at rate 2, okay? Now, how does this work? Well, essentially what you're doing, what you're sending, is you're telling the decoder a set to randomize over. So you get an assignment task 3, and you're telling them randomize over tasks 1, 4, 7, 12, and 15. And then they're randomly picking among those, and they don't even know what task you have. They just know it's not in that set, right? So to achieve this point, you're basically, the sets that you're telling them to randomize over are about half of the total tasks. So it takes about 1 bit when you construct this code book to tell them, to give them a sequence of these sets that they can randomize from. Okay. Now, but you still need some encryption. What you use the encryption for, 1 bit is used for the one-time pad. Okay. The extra bit is to randomly generate the code books in a special way. Because notice that even when you communicate this way, they're not really randomly picking from all of the other tasks. They're only randomly picking from some of the other tasks, right? So if you randomize your code books enough, you can make it all work out that they are actually randomizing over all the other tasks. Okay. Now, there's a trade-off. If you want, you can get away with a much smaller communication rate. You can get away with a communication rate of about 1 over k, approximately. But it's at the expense of a lot more common randomness, a lot more secret key. And so the way this works is you reduce the size of the set that you're telling them to randomize over until eventually you're just telling them which task to take, right? But because they're not randomizing very much privately, then you need to do much more randomizing of your code books. Okay, so you require a secret key rate of approximately log k, rather than just a constant 2, which was constant for all k. Okay, so all right. So the general idea here, we looked at how information theory could solve some simple cases, or at least give you insight into some communicating for simple cases of coordination. The idea would be, real networks aren't of this simple structure, and this probably isn't a very good model of how tasks are distributed in a network, but just a demonstration of how these tools might be used. Just a reminder of what we looked at: the non-adversarial case in three different networks, and then the adversarial case where we saw a trade-off between communication rate and secret key, and we also saw that some of these fundamental quantities came up. The minimum communication rate was mutual information. The minimum secret key rate was common information. Thanks.
Perhaps going back to the first half of your talk, because it's a simpler setting, what happens if you insist that there's no buffer and no code book? You just have to do things one experiment at a time, and then what you're interested in maybe use some randomness along the way, and then what you're interested in is just the entropy of this random variable that you send along the link. So it seems you can still do some things.
So you're allowing for still coding in the sense that you're getting away with the entropy, right? So if it's less than a bit, then you're going to use less than a bit, right?
So if you send a bit, but most of the time it's a 0, then that counts.
I see. So instead, it seems like instead you're saying rather than working with mutual informations, which is what you get out of this codebook method, you're using just entropies of random variables. So in other words, you're constructing a correlated random variable and sending it losslessly with entropy. I think you would end. Well, a couple of things. First of all, you'd end up with significantly higher rates, I think, if you did that. But also, there's another way to model this short delay in a network. You can say, suppose you don't want to have buffers at all, or you want to constrain the buffers to some limited size and say, we don't want more than this much delay. And people have looked at information theoretic problems from this perspective. I haven't really done it much, but there's work on source coding with fixed delay, and that would also be relevant here, I think.
So it might be sort of interesting because then it makes it so much simpler. Right? Here's something you can do maybe if communication doesn't always work or something like that. You just want it to be visible.
Yeah. Yeah, exactly. Yeah.
But measuring your cost in terms of the entropy is only realistic when you have repetitions.
Yeah, but
so you're already
but
buffering.
You see, you can suppose that the communication channel is smart, so it can send low entropy.
So sort of like
but you don't have to have. But the two people don't have to have any clever.
Sort of a separation. You want sort of a separation where you can give. You can have the channel coding is done at the entropy limit by some box that you don't have to deal with, and you so
just like when you talk to someone over Skype, right? I mean that's different. And I have a stupid question as well. Just about the motivation that you gave for the mathematical problem at the beginning. So.
For this thing? Yeah?
No, right at the beginning when you were talking about searching and assigning searches to
yeah.
So it seems to me in that application that there would be a lot more information content in what the actual searches were. So I'm just wondering if there's some.
I think a good model. I think a good model for task assignment, better than the one we've done here, would be to say you have a huge set of possible tasks, like all this possible searches or something, and you are given some subset of those to do, like some set of size k, and those involve like all of the keywords in your search query or something like that. Say, oh, you need to do. Here's the different parts we can break out this search into several different tasks, right? So then the computer in the network that's the controller for the network or whatever would not just be given a task to do, would be given a set of k tasks that need to get done out of the possible million tasks. And then you say, now he gets to choose who does all these tasks, but they just want to spread them out so everyone's doing one of them or something. And it's a really different problem, actually. I mean, it may sound the same, but it's really different because he now has a set of k out of a large number and gets to choose one for himself, whatever he wants, and gets to have them each do different things.
Right, so it seems that telling the other computer what the whole task is a lot more than just telling it it's task number 3.
Yeah. Well, if you're looking at all the possible tasks out of a million, then yeah, that takes that into account, right? Or out of hundreds of trillions, right? And that takes that into account. It's like the entire description of what you're supposed to search, right? But yeah, it's a different problem. Although you can still hack away with it with some of these same tools and find some interesting results. Actually, for the case I just described, and in the network where you just have in this network here, you can get an upper and lower bound that are pretty close to each other, actually. So.
If you go back to the star networks, same the original problem. You just need to find them different. I mean, the center one pixel, and the rest just need to be different. If you have a complete clip, if you have complete edges between them, does it help in any way?
Yeah, I think it would. If you just look at the 3-node case, if you had a third connection like this, yes, actually, it might even be solved in that case. It does help, but I mean it's hard to say. I guess you'd compare the sum rate.
Yeah, talking about can you beat the log k?
Beat log k. That.
You don't know, maybe you could beat log
Yeah, but maybe this is simpler.
Yeah, that's a good question.
More options.
Maybe you could. Yeah, I don't know. So if you just.
I mean, certainly monotone.
So yeah, that's.
If you have more edges. I mean, this is.
Ignore some of the edges.
Yeah.
That's a good question. Here's a good question. If you were just allowed any network you want, like you said, the complete graph. Yeah, what's the lowest rate? Sum rate. Yeah. Is it constant? Maybe it is. Cool.
And the complete graph is the best.
Yeah.
Okay.
As long as you allow bidirectional, whatever. Yeah.